Hi students, today let's continue with our topic. So today's topic is thermal conductivity. Thermal conductivity is defined as the amount of heat energy which is flowing per unit time through the unit area cross section of a material. From the amount of heat flow Q is equal to K dt divided by dx, we are deriving the thermal conductivity of the material K as Q dx divided by dt. We know the dt divided by dx is nothing but the temperature gradient of the material. Let us derive the expression for thermal conductivity. Consider the above shown diagram which has one end of plane as A and another end of plane as B. They both are at different temperature T1 and T2. T1 is of hot temperature and T2 is cold temperature. Now consider the mid cross section throughout the material is C. So, from the midpoint C to A, it gives the lambda distance, and from C to B, it gives lambda distance, which is totally 2 lambda. Lambda means mean free path in which the electrons used to flow. Generally, the hot side electrons loses its kinetic energy to the cold side electrons, so that both the temperature transportation makes the material to be neutral in temperature. So, the hot electron starts to lose its kinetic energy, whereas the cold electrons start to gain its kinetic energy. So how this temperature transfer takes place? Because those electrons within the material start to collide. This collision causes the transfer of energy. So based on this, we are calculating the average kinetic energy in both planes A and B. So at A plane, we are having the kinetic energy as 3 by 2 kT. This is derived from the ideal gas law. Small k is nothing but the Boltzmann constant, which has a value of 1.38 into 10 power minus 23 joules per Kelvin, and T is nothing but the temperature that is maintained in the material from A to B. So now coming to the B plane. So here the temperature is nothing but the actual temperature to the difference in the temperature. So the only variation in this expression is 3 by 2 K T minus dt, which gives the change in temperature. The excess of kinetic energy carried by the electron is nothing but the difference of the average kinetic energy from plane A to plane B. So on differencing both the equation, we are getting the expression as 3 by 2 K dt. Now coming to the another expression, number of electrons crossing per unit area per unit time from A to B. This is nothing but 1 divided by 6 small n V. N is nothing but the electrons that is taking place within the material, and V is the velocity of those electrons. After computing the excess of kinetic energy, now we are computing the excess energy expression, which is nothing but the product of excess kinetic energy to that of the number of crossing electrons. On solving those, we are getting the expression as 1 divided by 4 NV/kdt, which forms the fourth equation, which is the excess energy equation. So the deficient energy equation is obviously opposite to that, so we are giving the negative form to that, minus 1 divided by 4 NV/kdt. So from the above expressions, we could calculate the net amount of energy transferred from the A plane to the B plane per unit area per unit time. It is nothing but the capital Q, which gives the difference of the fourth equation and the fifth equation. So on solving the excess energy and deficient energy equations, we are getting Q as 1 divided by 2 NV/kdt, which forms the sixth equation. So already we have seen from the introduction of thermal conductivity, we have the amount of heat Q as K dt divided by dx. Here dx can be derived as the mean free path lambda. From equation 6, we could substitute Q as 1 by 2 NV/kdt. So now we need the expression for thermal conductivity. So we are taking capital K in one side. So we are getting the expression as capital K is equal to 1 by 2 NV K lambda, which forms the seventh equation. Generally, we know that for metals, relaxation time is equal to collision time. So, tau is equal to tau c. We already know the expression for tau as lambda divided by v. So, for lambda, we are deriving as tau v. So, this forms the 8th equation. So, on substituting 8th equation in 7, we are getting capital K thermal conductivity is 1 by 2 Nv squared K tau. Thus, we have derived the expression for the thermal conductivity. Let's continue in our next video.